Hello everyone, this is our lecture for Chapter 8, Confidence Intervals. Here are the learning objectives for Chapter 8. This is what we are going to cover, and this is what you will need to know for the next proctored quiz. Think of these learning objectives as your roadmap through the chapter and your study guide for the next quiz. So take a minute, hit the pause button, and read through these. In this lecture video, we will explore inferential statistics. We will begin our journey into inferential statistics with estimation. We will discuss point estimates and confidence intervals. After we select a sample, we know the responses of the individuals in that sample. The reason we analyze a sample is not to learn about the individuals in our sample, but to draw from the sample data some conclusion about the wider population that the sample represents. Statistical inference provides methods for drawing conclusions about a population using sample data. Because a different sample might lead to different conclusions, we can't be sure that our conclusions are correct. Statistical inference uses the language of probability to say how trustworthy our conclusions are. This chapter and the next chapter introduce the two most common types of inferences. 1. Estimation. And 2. Tests of significance, also known as hypothesis testing. We use estimation in two ways. First, with point estimates, and second, with confidence intervals. We will discuss both, since the information collected from a sample does not contain all the information in the population. We assign probabilities to our estimates. These probabilities serve as a way to measure what will happen if we estimate the value of the parameter many times and provide a measure of confidence in our results. The goal of statistical inference is to use information obtained from a sample and generalize the results to the population that is being studied. The first step in estimating the value of an unknown parameter is to select a random sample and use the data from the sample to find a point estimate of that parameter. A point estimate is a sample statistic that estimates the value of an unknown population parameter. A point estimate is a single value that best describes the population of interest. For example, the sample mean M is an unbiased point estimate of the population mean mu. The sample standard deviation S is an unbiased point estimate of the population standard deviation sigma. The following are examples of point estimates. The number of Facebook friends among people under 30 is M equal to 220 with a standard deviation of S equal to 18. The advantage of a point estimate like the sample mean is that it is easy to calculate and easy to understand. The disadvantage, however, is that we have no clue as to how accurate this estimate really is. In order to deal with this uncertainty, we can use an interval estimate, which provides a range of values that best describes the unknown population parameters. Why are most population values or parameters unknown? Well, the size of populations make it nearly impossible to gather that much data. Most researchers do not have the resources or the time to gather population data. Why do you think census data is collected every 10 years? Imagine how much it would cost to collect census data every year. So, how accurate is a point estimate of the mean? A way to answer this question is to ask how much do means from a sampling distribution vary? One indication of this variation we know is the standard deviation of the sampling distribution of sample means. Like any standard deviation, it tells us how much scores in the distribution typically vary. In this case, the scores are sample means. Since our interest is in making an estimate of the population mean, any variation is error. So the amount of variation is the amount we expect sample means to be off or in error as an estimate of the true unknown population mean. Remember that sample means vary from sample to sample. We know that if we take different random samples from the population of interest, we will get different sample means for each random sample. This difference is what we call sampling error. The point estimates, these sample means, would be reasonably good guesses of the population mean. But due to the variability in sample means, we are better off reporting a range or interval of values with some measure of the likelihood that the interval includes the unknown population mean. In statistics, we construct intervals for a population mean centered around a guess. The guess is the sample mean, or the point estimate of the population mean. A confidence interval for an unknown parameter consists of a range of values. The level of confidence represents the expected proportion of intervals that will contain the parameter. The level of confidence is the proportion of times that the interval contains the population mean if repeated samples are obtained. The three most commonly used confidence levels are 90%, 95%, and 99%. The higher the level, the lower the risk that our interval does not contain the parameter. A confidence interval is a range of numbers, such as the mean number of Facebook friends is between 200 and 240. A confidence level specifies the proportion or probability that the population parameter will indeed lie within that specified range of values, such as we are 95% confident that the true population mean number of Facebook friends falls within a range of 200 to 240 friends. There is a 5% probability that the true population mean is less than 200 or greater than 240. So a 95% level of confidence implies that if 100 different confidence intervals are constructed, each based on a different sample from the sample population, we will expect 95 of the intervals to include the population parameter and 5 to not include the parameter. The most commonly used z-critical values for what we call a two-tailed test, two-tailed we'll talk about in Chapter 9, they are 90% confidence level, z equal to plus or minus 1.65, for a 95% confidence level, z equal to plus or minus 1.96, and for a 99% confidence level, z critical is equal to plus or minus 2.58. Confidence interval estimates for the population mean are calculated as a point estimate plus or minus a margin of error. The margin of error is the expected difference that we think is possible between our sample statistic and the population parameter. The margin of error of a confidence interval estimate of a parameter depends on three factors. Level of confidence. As the level of confidence increases, the margin of error also increases, and vice versa. Sample size. As the size of a random sample increases, the margin of error decreases. This is a consequence of the law of large numbers, which states that as the sample size increases, the difference between the statistic and the parameter decreases. And the third, standard deviation of the population. The more spread there is in the population, or as standard deviation increases, margin of error increases. Now the question is, how do we construct an interval? The formula to construct a confidence interval is as follows. Sample mean M plus or minus Z critical times sigma divided by the square root of n, or sample mean plus or minus a margin of error. 95% of all sample means that will result in confidence interval estimates that contain the population mean is written as M plus or minus 1.96 times sigma divided by the square root of n. If population standard deviation is known, we use Z critical value and sigma to calculate standard error. If population standard deviation is unknown, and if n is greater than or equal to 30, we use Z critical value and S as an estimate for sigma to calculate the standard error. Remember, S is our sample standard deviation. If n is less than 30, then we use a T critical value and S as an estimate for sigma to calculate standard error. So the interpretation, here's an example. A 90% confidence interval indicates that if we obtained many simple random samples of size n from the population whose mean mu is unknown, then approximately 90% of the intervals will contain mu. So for example, if we constructed a 90% confidence interval with values between 12 and 18, we would interpret the interval as, quote, we are 90% confident that the population mean mu is between 12 and 18. Be sure that you understand that the level of confidence refers to the confidence in the method, not the specific interval. So a 90% confidence interval tells us that the method will result in an interval that contains the population mean mu 90% of the time. It does not tell us that there is a 90% probability that mu lies between 12 and 18. So to summarize, confidence intervals are a type of inferential statistic that calculates an interval estimate for an unknown population parameter. The larger the sample size n, margin of error decreases, which leads to a narrower confidence interval and vice versa. The higher the confidence level, margin of error increases, which leads to a wider confidence interval and vice versa. The higher the standard deviation, margin of error increases, which leads to a wider confidence interval and vice versa. So this concludes our coverage of Chapter 8.